Mhm.
I have a question for you. Which screen are you watching? Well, which screen is in? Which screen I'm sharing? The one where it's only the slide, or the one where is the picture of you, the video of you, and the video of me?
Maybe only the presentation.
Ah, okay, perfect.
Okay, let's get started. Hello, everyone. Welcome to our Nanomotor mini talk. Today, we are very happy to invite Gerardo Salinas to give a talk on our mini talk. And Gerardo comes from the University of Bordeaux. He's working with Professor Alexander Kuhn. He will talk about the Lorentz force driving autonomous Janus swimmers. So let's welcome Gerardo to share his research. So please go ahead, Gerardo.
Thank you very much for this kind of introduction. Yes, I'm Gerardo Salinas, and I work with Professor Alexander Kuhn. And on behalf of all the authors of this work, we really appreciate the invitation of this for this presentation. So I'm going to talk a little bit about this work about Lorentz force-driven autonomous Janus swimmer. So let's start with a small introduction. So mimicking dynamic systems at different size scales has been an interesting topic among the scientific community recently. Micro and nano swimmers are devices that can transform different types of energies into motion. In order to do that, the symmetry needs to be broken, either by changing the particle composition, the shape, or the surface reactions. These devices present interesting applications in environmental remediation, sensing, cargo delivery, or to study or evaluate collective behaviors. The mechanism of propulsion of these devices, it could be by bubble propulsion, self-diffusophoresis, or self-electrophoresis. These are based on the asymmetric release of bubbles due to a catalytic reaction, or by the self-generation of concentration gradients or electric fields. Another alternative is to propel these swimmers is to apply an external and non-invasive perturbation, either by applying light, an electric field, or a magnetic field. In particular, magnetic field is really interesting because either you can move the particle by a simple pulling mechanism, or by alternate pulses of the changing the polarity of the magnet, you can make rotors or make undulatory motion. In this work, we are really interested in coupling the self-electrophoresis mechanism in the presence of a magnetic field. The synergy between these two mechanisms allows to induce a Lorentz force that in theory will give enough force to propel the swimmers. So how does this work? First of all, we need a self-electrophoretic swimmer. So this was built by attaching a magnesium plate and a platinum plate. In order to give some space, and we can explain a little bit about this mechanism, let's imagine that we are connected these two plates by a wire. So in an acid media, magnesium oxidation and proton reduction in the platinum surface occurs spontaneously with a standard redox potential difference of 2.34 volts. This redox reaction causes two different ion fluxes. The first one is the magnesium 2+ that flow through the anode from the anode to the cathode in order to keep electron neutrality. And the second ion flux is cations from the surface of the plate to the bulk of the solution, or the bulk of the solution to the plate. It's really important that we can see that the ion flux is different in the center of the plate and at the edges of the plate. As you can see, in the center of the plate is perpendicular to the plate. However, in the edges is quasi-parallel. And this is the first ingredient for the magnetohydrodynamic flow, because when in the presence of a magnetic field, these ion flux in the edges of the plate will fill the magnetic field, and this magnetic field will induce a Lorentz force according to the right-hand rule, causing the formation of horizontal magnetohydrodynamic flows in each plate. If these plates are close enough, then the sum of these vortices or these horizontal magnetohydrodynamic flows will create a force. This force in theory should be enough to propel the swimmer. So the first part of the work was to evaluate if we can form this magnetohydrodynamic flow and visualizing this magnetohydrodynamic flow. So in order to do that, we build this setup when we have a magnesium plate, a platinum plate connected by a wire. We immobilize them in the center of a Petri dish. We put a solution of sulfuric acid and SDS. Then we place the Petri dish in the middle of a magnet. We spread some glassy carbon beads in order to track the motion of the formation of this magnetohydrodynamic flow. And as you can see, two circular patterns are formed as function of the orientation of the magnetic field. We can observe when the south pole is faced up, we can observe a clockwise and anti-clockwise motion, either in the platinum or in the magnesium. And when we invert the orientation of the magnet, we can observe the opposite trajectories. When we analyze the trajectories of these tracking particles, we can corroborate this clockwise and anti-clockwise motion as function of the orientation of the magnetic field. And we can also evaluate the speed. And we observe that the speed shows some periodicity. This periodicity is correlated to the position of the particles and the surface of the plate. When the particle is in the outer part of the plate, the speed is relatively constant and low, 1 millimeter per second. Once that the particle enters the middle part between the plates, the speed increases. This is the first proof that we can form this sum of vortices to create a force to propel the swimmers. Once that we perform these experiments, we decide to use the swimmer in a static setup. Once again, we can observe the formation of these circular patterns in the surface of the plates. We observe that these circular patterns are function of the concentration of sulfuric acid the radio of these circles increases as the concentration of sulfuric acid increases. And this is just because an enhancement of the reactions that occur in the plates. Once again, when we track the particles, we can see that we observe some periodicity. In the outer part of the plates, the speed is low and almost constant. Once that they reach the center of the devices, the speed increases drastically. This maximum speed is correlated to the concentration of sulfuric acid. We can observe a linear tendency as the concentration increase of the maximum speed in the center of the device, reaching a maximum of around 1.7 centimeter per second. This linear tendency is independent of the orientation of the magnet, so there is no problem because of that. Once that we observe or we corroborate the formation of this magnetohydrodynamic flow, we decide to evaluate the motion of our swimmers. In the absence of the magnet, the swimmers just move randomly in the surface of the solution due to a formation of a bubble propulsion with a relatively low speed. So in theory, the formation of our magnetohydrodynamic flows will produce a force strong enough to propel or to enhance this motion. In addition to this, as I mentioned before, we have an extra ion flow that it comes from the magnesium plate to the platinum plate in order to keep electron neutrality. This flow is along the edges of the swimmer. Once that we put the magnet, this flow will form another Lorentz force that is gonna create an additional torque force that is gonna cause that the swimmer starts to move in circles. In order to corroborate this, we evaluate the motion of 4 of these swimmers. As we can see, when the North Pole is face up, the swimmers show clockwise motion, whereas when the South Pole is face up, you can observe anti-clockwise motion. These swimmers present 2 types of motion. Either in the center of the magnet, there is a semi-perfect, perfect circular motion. This is caused because the magnetic field is practically homogeneous, or that the swimmer starts to go to the edges in semicircular motion. This is because the swimmer starts to look another points of the magnetic field, and then he reaches a point where the magnetic field is not completely homogeneous. As we can see also, the speed increases in 2 orders of magnitude in comparison with the swimmers in the absence of the magnetic field. After this, we try to see if we can transport this, this phenomenon to a smaller scale. So for that, we cover half of a magnesium wire with platinum black. In the absence of the magnetic field, our Janus particles move randomly in the surface of the solution due to the bubble propulsion. Once that we put the magnet, we can observe the clockwise and anti-clockwise motion with an enhanced speed. And in function this motion is function of the orientation of the magnetic field. Finally, since the motion is function of this additional torque force, we can tune this torque force by changing the composition of the swimmer. So in order to do this, we just cover 20% of the swimmer with platinum black or 80% of the swimmer with platinum black. So when we cover only 20%, we observe a semicircular motion. But when we cover the 80%, we observe a perfectly good circular motion. Again, both of these motions are function of the orientation of the magnetic field. Why is this happening? This is happening because there is a competition between the magnetohydrodynamic effect and the additional torque. So when we have less platinum, most of the electrons are consumed by the reduction of the protons in the magnesium. Thus, the predominant effect is the magnetohydrodynamic. When we have enough platinum to reduce protons, there is a considerable flow of electrons from magnesium to the platinum, causing that there is a considerable flow of magnesium 2+ to platinum. Then this torque force is predominant. So as conclusion, we were able to power magnesium platinum Janus swimmer propulsion by the magnetohydrodynamic effect. This magnetohydrodynamic flow is induced by the orthogonal combination of an external magnetic field and the ionic flux associated to the spontaneous redox reaction of magnesium and platinum. We observe highly controllable clockwise and anti-clockwise motion as function of the orientation of the magnetic field. We can control the directional motion of macro and micro devices. And this new method or this new mechanism is an easy and straight way to boost the propulsion speed of self-electrophoretic swimmers with a permanent magnetic field. So I just want to thank Alexander Kuhn for letting me work in this lab, Dr. Lore Bouffier, Professor Nestor Sojic, Patrick Garrigue, and Kostya for all their input in this work. To the rest of the people in the lab, thank you very much. And thanks to all of you for your kind attention.
Okay, thank you. Thank you. Thank you for your last talk. And now we're going to the Q&A session. And if the audience has a question, please feel free to unmute yourself and ask the question. We got a question from the chat box.
There is a...
The audience asked, can these motors move underwater?
We haven't tested the motion of these swimmers underwater. Well, we haven't tested if the mechanism that we are proposing can move objects under the water. In theory, if the object is small enough and the force of the magnetohydrodynamic flow is strong enough, it can happen. We can move the particle under the water, but we need to consider that we need to beat the friction of the surface of the plates or the surface of the bottom of the flask where we place the swimmers. So it's something that we need to evaluate in future experiments.
Okay, thank you for your answer. Any more questions from the audience?
Oh. Oh la la. I hope that everyone can see this question. The Lorentz first perpendicular to the velocities. Okay. The energy for this motion, yes, I agree with you. It doesn't come from the magnetic field either, because yes, it doesn't come from the magnetic field. all this energy comes from these reactions that we have spontaneously from the oxidation of magnesium and reduction of protons. And these reactions are thermodynamically favorite. As we know, when we place this magnetic field, according to the, let me go back to that part. Yeah, to this part. So, according to the right-hand rule, if we have an ion current here, there is this one, in the presence of a magnetic field, this is a vector product, so we will have this Lorentz force. Each of the plates generate their own horizontal magnetohydrodynamic flow. And as we expect, and also as we observe, when these two are close enough, we can have the addition of this force. I agree with you in some where did you say it? The electrons are symmetrical. This, where is it? Swimmer synergy. This kinetic energy, well, this energy, chemical energy that we are given by these reactions, we can control it by the concentration of sulfuric acid. We can tune these reactions, and then if this vector is bigger, then the product of vectors is gonna give us a bigger Lorentz force, okay? This magnetic field is always constant, so right now in this work, we're only playing with this vector, as we can see it. We are not, how can I say it? We are not taking energy from nowhere. The energy comes from this current and how this current is affected by the magnetic field, okay? I hope I answered this question.
Okay, thank you for your answer.
Someone else? Okay. The Lorentz force plays a role of constant torque. Well, we don't mention it. I think Professor Kuhn have a question.
No, go ahead. I just had a comment to the previous question, but it's okay. Go ahead.
Okay, so first, the Lorentz force plays all of these forces that we are presenting are Lorentz forces. This magnetohydrodynamic flow is caused by the formation of a Lorentz force, and this F that we are showing here is just the sum of both of these vortexes. The constant torque in here is also a Lorentz force, because if you use the right-hand rule, these ions flux and this magnetic field will produce the Lorentz force that is here represented as F, represented here. So yes, all of these forces are Lorentz forces. We just decided to put different names in order to not have any, how can I say it, confusion. Now, did I measure the mean square displacement? No, we didn't calculate the mean square displacement. I think it would be a good idea to measure this parameter to see if the mechanism is ballistic or other types of mechanism, for sure. Thanks. Okay. Do you want to make your comment, Doc?
Yeah, just a brief comment. why the swimmer speed globally is increased when we have the presence of the magnetic field. There's also another effect that is maybe a little bit more indirect. I mean, I agree with what you said, that the energy comes from the chemical reaction, and we are kind of focusing the chemical energy into this Lorentz force vector that is combined in the middle of the two parts. But there is also a kind of indirect, more hydrodynamic effect, because as you have shown very nicely with your tracking particles, there's a huge and very aggressive or efficient hydrodynamic flow around the swimmer, which is kind of renewing constantly the concentration profiles around the swimmer. So you can see the particles there move around like hell. So there's a kind of a cleaning effect. So you can, with this magnetohydrodynamic effect, you can constantly renew the chemical gradients around the swimmer. So you remove the bubbles from the magnesium, which otherwise would maybe passivate the magnesium for a while. And this also can help to increase the global speed. That's at least an additional effect that can be mentioned, I think.
Yeah.
Okay, thank you, Professor, for the clear explanation. So any more questions? If no more questions, we would like to thank Gerardo again for his nice talk. Thank you, Gerardo.
No, thank you very much, guys.
So we would like to conclude this talk and thank all the audience for listening. Hope to see you guys in the next week.
See you.
See you.